Welcome to the third section of this MBT Science Trilogy. If you're just looking at this for the first time, the trilogy, that is, for the first time, we'll notice that we have two sections have been done previously. The first was Science, Math, and My Big Toe. The second was the logic of virtual reality. And now today, we're going to do the logic behind the scenes. Details of how and why physical matter reality's rendering engine creates our reality. And I'm going to do that with three examples. One's going to be Schrödinger's cat, the other is going to be the Zeno Effect, and the last one will be the double slit experiment. Okay, well, let's get going. First, as an introduction, I know this is an awfully busy chart. It's like reading a book to look at my charts, but I wanted to get it all on one slide because each line kind of interacts with the other lines, and it's better to see it all in one. And I didn't mean my briefing to be pretty. I meant it to be informative, something that you could look at later and understand what it is that I'm saying here. So this will just catch us up a little bit, remind us of what we said in 1 and 2, and kind of set up the field for discussing the mechanics of computing reality. First of all, I'd like to point out something that I think I've probably not said before, but it's an obvious thing, and that is that in mathematics, we have analytical functions. They're also called continuous functions, okay? And that's in contrast to digital functions, which are functions that don't have smooth lines, but have little jagged lines, pixelated functions. Now, for an example, you look at a parabola, and in a continuous analytic curve, that would just be y equals x squared. Okay, so if you put a value of x, square it, and then put that value on y, you will draw a parabola. Okay, well, this is a continuous function, and it's an analytical equation. This is an ideal. Now, to contrast that with a digital curve, a digital parabola, that's where x and y now are not continuous functions, but you will vary x by a certain amount each time, some delta x. So x jumps by some delta x amount, and then each time you compute a y. So you'll get a curve that looks very much like the continuous function parabola, except it'll have little zigzags in it, depending on how big or small your delta x was. If your delta x is very, very, very small, it will look just as smooth as the continuous function. But as it gets bigger, it'll get you'll see a little zigzag in the line, and if delta x gets big, you'll see big zigzags in the line. Okay, now, the way we look at this is really just backwards of the way it is. We believe that our reality is continuous. We believe that space is continuous and time is continuous. Well, because we believe space and time is continuous, we believe that analytical functions like y equals x squared represent physical reality, but they don't. Our physical reality is computed in a computer. It's the digital curve that really represents our reality. Well, we tend to think, well, I'm going to fire a cannon in a place where there is no air, and if there is a uniform gravitational field, that cannonball will travel on a parabola. And if I model that in a computer, it's the analytical continuous function that is the truth, or the way it is, and the digital one, which is the approximation. In actuality, it's just the opposite. Our reality is created in a computer. Much of the computation is is what shall we say, numerical methods is what we call them. That is using a computer to solve analytical functions, numerical methods. So have in your mind that when you think about our reality, reality is pixelated, just at a very, very, very small level so that we don't notice it. It tricks us into thinking that our reality is continuous. And because we think that, it becomes a belief. Because this is our experience, we don't see the zigzags, so we have a belief. And you can call it a scientific belief or a cultural belief, but it is a belief we have that we live in a continuous reality, continuous space, and continuous time. The other thing I would like to say about that is that when we actually try to model our reality, we find that using continuous functions never seems to work except for very, very simple things. The real world isn't modeled well by continuous functions. The real world is only modeled well digitally. Now, here's what I mean. If we fire that cannon in the real world, well, there is no uniform gravitational field. The gravitational field changes from place to place and spot to spot. The Earth is not a perfect sphere. The makeup of the mantle is not perfectly a constant density. So gravity changes a lot. Secondly, there is air and humidity and lots of other things, smoke and particles floating around in our atmosphere that interact with that cannonball. Yes, the interactions may be small, but if we're trying to get an accurate description of where that cannonball actually goes, then we have to take all those things into consideration. Also, that air density varies with with weather patterns. It varies with altitude. It's actually in constant fluctuation. So for us to make a really accurate model of that cannonball, we go to a computer. Well, you see why that is? Because it's actually done in a computer to begin with. The continuous functions, the analytical math, is actually the approximate math. It can give you approximately the way a cannonball would go because the air is a small factor and the variations in gravities are small factors, so it's an approximation. But the computer, the digital curve, can get you much closer to the reality. So I think this is interesting just because it is very backwards from the way we look at it. We say those analytical equations, that's right. And those digital ones, well, they just approximate the correct analytical ones. They're the ones with errors in them. And that's really not the way it is. All right, let's move on. Given charges at a specific location, electric field equations can predict forces on a unit charge at various locations. The field does not exist as a physical thing. Okay, now we say that those charges create an electric field, and that electric field produces a force on a unit charge that's in some other location. It affects that other charge. If the charges are the same, it pulls them together. If the charges are opposite, they push apart. Okay, but this field, the thing we call the electric field, does not exist as a physical thing. It has no material reality. It's a model, a useful model, but most people, including physicists, believe it's a physical thing. Well, 5G is coming, and there's going to be all that electromagnetic radiation, all those fields out there, and they're going to be going through our bodies, and they're liable to cause health problems for us. Well, you can read about that, and I'm telling you, they don't really exist. Well, they don't really exist, but the health problems do. You see, because there are charges out there that are moving, and moving charges affect other charges that are nearby or that that they're close to, depending on how far away they are. So that's a fact. That's a calculation. That's because that's the way the rule set requires this virtual reality to behave. That's the rule set. So the damage done to our bodies is a real thing, even though there are no fields. But scientists and biologists and other people say, oh, it's those electromagnetic fields that are damaging your body. You see, it's an easy thing to say, but it's just not true. Okay, physicists try to interpret their analytic approximation to reality in terms of material physical reality. That creates problems. In other words, they look at their equations and then try to say what those equations mean in a material physical world. And that creates problems. What happens is we end up with things called wave functions. Wave functions don't exist. It's just it's a metaphor for the mathematics that's used in quantum physics. There are no wave functions in the physical world. It's not a physical thing. The same with collapse. Collapse of the wave function to a physical event, to a physical particle. There is no wave function, there is no collapse. And we're going to see that in this Schrödinger cat explanation just in a little bit. So things like wave function and collapse and stretchy space-time, space-time stretches when you have a large mass. And the analog or the metaphor that people always tell you, it's like the bowling ball on the trampoline, okay? Fields that I just discussed with electric fields, but fields of all sorts, even morphic fields, anything that's a field doesn't exist. Action at a distance doesn't exist. It's just computed. Okay, electrons, atomic and subatomic particles don't exist. They're just models. Okay, we know that if we can make measurements in experiments and we can find momenta with charge, and we say, oh, well, there's a little chunk of mass with a charge, because our experiment can make it move up and down with an electric field. It must have charge, and the momenta can actually produce little forces when it hits something, spurt of energy. So we look at the experiment, we look at the results, and then we make up a model and say it looks as if there was a chunk of mass with a charge, but it's only an as if. You see, we're just measuring the results. We're not really measuring the particle, we're measuring the results of the particle, the effects of the particle. So an accurate way of saying that would be our experiment seems to function as if there were electrons, as if there were little particles of mass with a charge. But it's just an as if. And if we left it as an as if, that would be fine because it's a very useful model. But when we begin to forget the as if and think that electrons are little chunks of mass with charge, then we get ourselves in trouble because, as quantum physics tells us, they're not like that. They don't work that way. They're probability distributions. They're numbers. They're something that's computed in a virtual reality. Okay. So, for example, some more silliness that you get when you try to look at an equation and come up with something physical. In quantum mechanics, the cat, Schrödinger's cat, is neither dead nor alive. It's a potential cat that is in a superposition of both states. It's a superposition of dead and alive. Well, that doesn't really make any sense. That's a silly thing to say. And it's a common belief. And most quantum physicists believe the cat is in a superposition. But that's not so much a potential cat, because that was actually a furry little creature that we stuck into that cage. There's a real cat in there, not just a potential cat. If it were a potential cat, it could be in superposition of both states. But it's a cat in our reality. A virtual cat, I'll give you that, but it's a cat from the viewpoint of the avatars. Okay, also from the double slit, particles somehow interfere with themselves. When they go through one of the slits, we don't know which one, then they somehow interfere with themselves and create an interference pattern. Well, physicists say all kinds of strange things, like the particle goes through both slits at the same time and interfere with themselves, or other equally silly things. Others realize it's silly, so they just say, well, it's just weird physics. We don't know. It's just silly to say that the particle interferes with itself. It's just a single particle. How does a particle interfere with itself and produce an interference pattern? So they just call it weird science, which means they don't understand it and they've given up trying to understand it. And then lastly, let's look at relativity. I haven't mentioned it yet, but I've mentioned that quantum physics is understood to be probability, because that's the nature of our reality. I think I talked about that last time in the logic of virtual reality, that it's natural for our world from the avatar's view that we would see particles as probability distributions, because that's indeed how they function behind the screens. It is. Our model is not a bottom-up model. It's a top-down model. And as a top-down model, it is probability. That's how it works. It's that random draw from the probability distribution of the possibilities. That's the collapse of the wave function. All right. So, relativity. Relativity talks about space-time curves around mass. Okay. Newton's gravitational theory just had two masses attracting each other. And that was pretty simple. It says all mass attracts all other mass. And if somebody says, well, why? Why does mass do that? Newton would have said, I don't know, just like physicists say today. If you ask a physicist, why would mass attract other mass? They'd say, well, I don't know. And now they say, oh, well, it doesn't. We've got a better model now. We have relativity. Space-time curves around mass, like that bowling ball on the trampoline, and then you have a couple of balls on that trampoline with that bowling ball, and they just roll right into that bowling ball because they're rolling downhill on that trampoline. That's how gravity works. And then if you said, well, tell me, why does mass warp space-time? Why is space-time elastic around mass? And they would say, no, I don't know, just like Newton would have said about his theory. They have no idea. So all they've done is replace one model with another model. Neither one has an explanation. Both of them are just models made up, okay? No explanation, just like the old model. But this model actually is better because it allows us to compute more things. We can, it allows for gravitation, it allows for relativistic effects, but still, there's no explanation about why space-time would do that. The problem is, if physicists realize that it was just a model and this space-time is elastic and that's what creates gravity, if they knew that that was just a model, and in some sense they do, that would be fine. But pretty soon they believe it. They believe the substrata, we'll say, beneath this reality is space-time. There's this space-time out there, and gravity is made by space-time. Like space-time makes gravitation. It doesn't. Gravitation is a rule in the rule set. It's computed. And Newton's model showed a simple way that it was computed, and Einstein's model shows a more complex way that it can be computed. But both of those things are what we'd say, downstream logical consequences of the fundamental idea. Okay. So relativity and quantum mechanics both do not represent fundamental science. That's why you got all the math. If they represented fundamental science, you wouldn't see much math. All you'd see is logic, just an explanation. But relativity and quantum are knee-deep in math. If you're not advanced in math, then you won't understand either one. It's required. That little toe Einstein was searching for was that fundamental logical understanding that would underlie both relativity and quantum mechanics. It's consciousness. Consciousness is the fundamental substrate upon which all else is built. So that's another reason for scientists realizing that relativity and quantum mechanics weren't really at the bottom of the pile. They were still logical consequences of something more fundamental. Not only do they conflict with each other, but they're both very mathy, which means they're downstream. They're not fundamental science. Consciousness is the fundamental substrate upon which all else is built, including relativity and quantum mechanics. All right, let's get on with Schrödinger here. That's enough intro. I just want to get your mind kind of thinking in the right way, try to shake you out of your habitual materialistic thoughts there. All right, so here is going to be a Schrödinger's cat thought experiment. Now, what you see in front of you is a hemisphere, a dome. That's going to be our cat house. And this cat house is actually a house that houses a cat. So don't get too excited about a cat house. We're going to put a cat in there. And well, actually, I'm not going to put a picture of a cat in there because the whole point is to kill the cat. And that's not very sensitive. So this is going to be an invisible cat. You're just going to have to imagine that the cat's in there because invisible cats, they won't be hurt. So there's a cat that sits in there, right? Curled up around that little red spot in the middle. Now, this little red spot here in the middle, that's right here. This red spot is a radioactive source. And a radioactive source is radioactive because it throws particles off. Particles just shoot off of it, one after the other, but they shoot off at all different directions. So a particle may zing up this way, and then it may zing out that way, and then it might zing out this way. It's random, equally probable to go off in any direction. Now, here, this other little red spot, that's the Geiger counter. That's a sensor. A Geiger counter is a thing that when one of these little particles that's been thrown off hits a Geiger counter, it creates a little electrical pulse, makes the Geiger counter buzz or makes a counter count. It can trip a switch. And in Schrödinger's very devious and dark mind, it released poison. So it hits the Geiger counter. The Geiger counter sends an electrical pulse that dumps a bunch of poison into this poor cat's house, and the cat dies. But it only dies if one of these particles from this radioactive source flies up here and hits that particular spot. Okay? If the particle flies up and goes over here, well, nothing happens. No electrical signal is created in the Geiger counter. No poison is dumped into the cat house. All right. So here are the probabilities. Okay, if the probability of a dead cat, it's basically the area of this Geiger counter divided by the area of this hemisphere, right? That's the probability that a particle coming out randomly is going to hit somewhere. Okay, we're only going to look at particles that come up into this half of the sphere, this hemisphere. The other particles that fly down out of the hemisphere, well, we'll just ignore them. We're only going to look at the particles that fly up. That's why I have over here a little R over 2. That's the number of particles entering the upper hemisphere, because R is the number of particles per unit time leaving the radioactive source. Half of them are going to go in the bottom hemisphere. The other half are going to go in the upper hemisphere. So anyway, so if we take the area of the hemisphere and divide that into the area of this, then that's the probability that some random shot that could hit anywhere inside this hemisphere is actually going to hit here rather than any place else. It's this area divided by all the rest of the area. All right, and that's what we have over here. It's the area of the Geiger counter over the area of the hemisphere. And here I just expanded that a little bit. I've taken the area of a sphere, divided it by 2 with the 1/2, subtracted this little area of the Geiger counter off of it. So that's all the area of the hemisphere except for that little bit of area. And then that defines this AG over AH, A, the Geiger counter area of the hemisphere. All right, and here it is expanded, like I say. Now, down here I have R's, the rate, the number of particles per second that are going to leave this radioactive source. That's how radioactive it is. T, that's the experiment in seconds. It's going to start at T equals 0. At T equals 0, we throw in the cat, throw in this particle, this radioactive source, and that's when it starts, T equals 0. So let's look down at the bottom here. We said that the probability that the cat's going to die from the very first particle is the area of the Geiger counter over area of the hemisphere. Now, we also know that if the cat's alive, in other words, if that first particle hits someplace else on the hemisphere and didn't hit the Geiger counter, that's going to be 1 minus the probability that it hit that Geiger counter. See, P dead is the probability it's going to hit the Geiger counter. That's what this is, P dead. Probability it's going to hit that Geiger counter. Now, 1 minus that probability is after one particle goes out, the cat's still alive. It's going to be 1 minus P dead, right? Because the cat's either dead or alive. All right. Now, I'm going to fire my second particle out. If my second particle also misses the Geiger counter and hits someplace else in the hemisphere, then it's going to be 1 minus P dead times 1 minus P dead. Those two probabilities multiply because it missed the cat on the first particle and it missed the cat on the second particle. And so you just multiply them. And after n particles have come out, then it's 1 minus P dead to the nth power. You see, so if it's 100 particles have come out, then 1 minus P dead to the 100th power is the probability that the cat is still alive. All right, so that's how all this works out. Again, here the R is divided by 2 because the rate at which particles leave the radioactive source, only half of them are going to leave it and go up to this upper hemisphere. All right, now that I've kind of set up the cat experiment, let's go see how it works out. Okay, now here's a spreadsheet. And if you look at this spreadsheet, here's going to be where we take our measurement here. Measurement T seconds after experiment starts. So it starts at T equals 0, and this is a column for seconds, and it's all seconds until we get over 60 down here. And then so when we get over, here's 57 seconds, and the next one is 1 minute and 2 seconds, you see. So I just keep track of the hours, minutes, and seconds so that it's easier for you to see in these bigger numbers, because otherwise somebody tells you, 10,000 seconds, you won't have any idea what that is, because it's hard to divide everything by 3,600 in your mind. Okay, so here's the measurement that we're going to make. And in 1 second, okay, in 1 second, because I started with R equals 2, I can go up just a little bit and I'll show you here. R for particles is R equals 2. You see that? So that means 2 particles per second come from the radioactive source, and 1 particle per second comes up into the upper hemisphere. Okay. Now, 1 second, one particle. That's on the average. So one particle is hit, and we see the probability that the cat's still alive, which means the probability that that particle hits someplace else in that hemisphere is 0.999928. And the probability that the cat is dead is 0.000072. Okay. Now, here, I've converted this ratio. That's a probability alive and dead, and probabilities are just ratios. So I've converted it to probability expressed in integers that are greater than 100. It's exactly the same ratio. So if I do that, then the ratio of 0.999928 to 0.000072 is exactly the same as the ratio of 1,395,784 to 100. You'll just have to trust me on that, or get out your little trusty calculator and see how that works. But these two are in the same ratio as these two. So it's the same probability. It's just really hard to put 0.999 balls in a box, or to put 0.00072 balls in a box. And I like this little picture of the raffle box with balls in it because it makes it easier for you to understand, makes it less abstract. So I've just changed this probability into larger numbers with the same ratio. So no sleight of hand here. I'm just making them so that we can look at it as balls in the box. So in this case, after 1 second, it's like you had this box over here and it had 1,395,784 blue balls in it and 100 red balls in it. And the random draw from the probability distribution of the possibilities is a random draw between this 1,395,784 blue balls and these 100 red balls. If you pull out a red ball, cat's dead. If you pull out a blue ball, cat's alive. And that's the probability if you make the measurement at 1 second. Okay, now remember, making the measurement is what collapses the wave function to a result. Making the measurement means you jerk open the door to the cat box and you look in and see whether the cat's dead or alive. That's making the measurement. So we do that in 1 second, and you see the probability that the cat's alive is very, very high. But that probability is going to go down with time, because the more little bullets you spit out of that source, the higher the probability that one of them is going to hit that Geiger counter and the cat will die. All right. So it's like I've done this experiment all these times. Every row here is like a repetition of the experiment, but at a different time. So here's where I did the experiment, and I opened the door to see if the cat was dead or alive in 1 second. Here, 120 seconds. Here, 240 seconds. Here, 1,080 seconds. Here, 4,020 seconds. Okay, so that's, that 4,020 seconds, wherever it was here, that's, 1 hour, 7 minutes. So in an hour and 7 minutes, I open up that door, and these are the probabilities now of finding the cat alive or dead, which translates into 300 blue balls and just 100 red balls. So if in 1 hour and 7 minutes, I jerk open the door and look, 300 balls are blue, 100 balls are red. I take that random draw, and that cat is likely to be alive, but might be dead. I mean, look up here at 42 seconds, just 42 seconds. It was 505 balls for blue and only 100. So there's 5 times more blue balls than red balls, but look what happened. I got a dead cat. That's because randomness is random. You don't always get something under the fat part of the curve. So I can change the random numbers. What this column is the actual result of the random draw. What I do here is I have some mathematics, some random number generators in mathematics that do the random draw. It looks at, like here in this case, in this dead one, it looks at 505. If there's 505 blue balls and 100 red balls, and you take a random draw, what do you get? Well, in this time, I just happened to grab a red ball. So if I looked then, the cat would have been dead, even though it's 5 to 1 that would have happened. Well, that's what happens, you see. Now, I can push F9 here on my computer, and it recomputes all of those tests. In other words, it's like I did the experiment again. It's like, all right, let's get another 1,000 cats and another 1,000 boxes, and let's do it again. Well, you'll see here, let me lean up and do that. Here, hit F9, that's right, here. Now notice when I did that, we've got a dead up here when it's 1,243 to 100. Whoa, you know, but came out dead. Sorry, cat. You know, that's the way it is with random draws. Even if there's only one red ball in there and all the rest are blue balls, you could pull out that one red one, but most of the time you won't. So that's what's going on. So let me just let you look at these. Mostly you're going to get a lives up here. Occasionally we just happen to grab a red ball, but as we get down, look at this. Mostly we get dead, and we get down further and the cat's always dead, because now the probability is there only 100 blue balls to, you know, here at the bottom, 48,000 red balls. So it's very likely the cat's going to be dead by 24 hours. And we go up here in the middle someplace. Here's a point that I made up. If exactly 9,675.186 seconds, the probability is 50-50 as I compute it. Depends on how accurate my computations are, but you see it's 0.5, which means there's 100 blue balls and 100.0000123 red balls. Now, if we wanted to actually make that 100.00 whatever, we'd have to multiply each one of those by a much bigger number. So in any case, you see, so there's 100 of each, 100 red ones, 100 blue ones. It's a 50-50 chance. And that happens at 2 hours, 41 minutes, 15.186 seconds. So that's how long it takes before this cat has a 50-50 chance of being still alive, you see? Now, so take a look at these. I'm just going to punch this F9 button, and you'll see every time I'm going to do another random draw for all of these times. So all of these measurements would all be just single measurements, but I've got them all listed down here. Like I did the experiment once at 1 second, I did it again at 2 seconds, I did it again at 4 seconds, and I did it again, and here's all the results. I did all these experiments at all these different times. Okay, now if I press this F9, you can watch over here and see how what's dead and what's alive changes. Well, we'll maybe look at this part. Mostly alive, but a few dead in there, and maybe down here where there's more dead, right around the 50-50 chance. So that would be right here. There's one. See how the dead and the lives? There's another one, another one, another one. Ooh, that one really got dead just before at the middle there. Another one, another one, another one. See how that works? These are all random draws. So it's not guaranteed at any particular time that the cat would be either dead or alive. Even the very first second, if that very first particle out of that source hit that Geiger counter, the cat would have died on the first second. It's just not likely. So this is how let me go back to that. This is how the Schrödinger's cat actually works. Okay, you can read here. Well, let's look at this. I didn't show you this, but look at these probability lines. Here's the blue probability line, probability right at time equals 0 is 1. Cat's alive. Haven't started the experiment yet. Cat is resting nicely. As time goes on here, these are seconds, then probability the cat's alive goes down, 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 and eventually goes to 0, or very, very small. Okay. Never actually gets to 0, just gets to like 10 to the minus, something. So very, very small. Now here's the probability that the cat's dead. It's very unlikely the cat will be dead immediately. And it's 0 that the cat's dead at t equals 0. But then as time goes on, the probability of the cat dying goes up and up and up and up. So the way Schrödinger's cat works is you put the cat in the box, and then at any time you make the measurement, a random draw is made from a probability distribution of the possibilities, and that is what the virtual reality renders at that time. So if you happen at this point, let's say where we are right here, here's the first dead that occurs, at 20 minutes. If at 20 minutes in, even though it's much more likely 1,000, 1,104 to 100 that the cat will be alive, well, that time, that random draw pulled out a dead. And when you make that measurement at that time, you get a dead cat. Well, you got one this time when you made that measurement. Every time you do this, it's like a new random draw. You have another cat, it's a different random draw. The next cat's a different random draw. So every line here that we move across, every row, it's a new cat being looked at a different time. You see? Okay, that is Schrödinger's cat within a hemispherical domed cat house. That's how it works. These are the probabilities. It's just, the math is simple. That's why I did this, because it's simple that most everybody can follow this. It's just a very little bit of algebra here. And you see that there is no cat that's both dead and alive. There is no potential cat. There's no superposition of cats. There's just simply a random draw from the probability distribution of the possibilities, and that's the answer. Now, I'm going to also show you how this works in a double slit afterwards, but we're going to do this, and then we're going to do a Zeno paradox, and then we'll do the double slit, and that'll get just a little more complicated because the probability distribution just isn't a binary, dead or alive. Now, the probability distribution is something quite different. It's a interference pattern, and we can say why it's an interference pattern. Why should these single particles position themselves on the screen in an interference pattern? Why would the system do that? I mean, it could be a pattern on a happy face. It could be a little happy face pattern, and that would be more cheerful. But for some reason, the rendering engine decided that it would make those particles line up in an interference pattern. And there's a reason for that. The requirements, the constraints placed on the rendering engine made that necessary. It has to be an interference pattern to meet the constraints on the rendering engine. Okay, now next, we're going to go to the Zeno effect. All right, Zeno effect will be even shorter. It's a very simple thing. This is how you set up the Zeno effect. There's a system, and I'll just call the system A. And A can exist in two states. This is a quantum system. So it exists in quantum states, which means it's not a continuous slide from one state to another. It's either in one state or it's in the other state. It's a jump between states, okay? So it can be in two states, state A prime and A double prime. So it's just in one or the other of those two. Now, its normal state is in A double prime, but it can be energized into a state A prime. That just happens sometimes. As time passes, it eventually returns to its normal state, A double prime. So I'm just setting up the problem. Now, the Zeno effect has been seen and is applied to dozens of things. It could be an atom. This could be an atom of some sort. Could be a hydrogen atom with, with two states, and it could get some energy and excite the electron up to a higher orbit, and then it drops down. Those could be the two states, or it could be something else. I just may put it in very general terms here because the Zeno effect applies to dozens of different systems. They're just systems that are in one state or another, or multiple states, and get energized. So now let's see. These curves look a little like the Schrödinger cat curves from probability. So here's our system. And this is what I already said up here. I've just repeated it in case you can't remember it. It's just up here repeated again. So this state has been energized. We're going to measure it. So we take our nifty state measuring tool and we measure A. And we go, I found A in A prime. Okay. Now what happens if I wait for 100 seconds, time down here, if I wait for 100 seconds and I measure it again, well, the highest probability is I'll find it back in A double prime, which is its kind of normal state that it stays in most of the time. Because the probability of it being in A prime starts to go down, 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 down until it goes to zero. And the probability that it's A double prime goes up, up, and up until that's where its state is. But we threw a little energy at this thing and then we measured it, and there it is at A prime. All right. Now, here's what's going on. Every time a measurement is made to determine the state of system A, here's how the larger conscious system, here's how the rendering engine calculates this behind the scenes. It takes a random draw from a binary probability distribution to determine which state it's in. And if it's in A prime, that's the excited state, it begins a clock ticking for how long it's likely to remain in that state. So think of computer code now. We go down through computer code and we get an if-then statement. If in A prime, then start the clock. Okay, simple thing. So we measure this and we get A prime. If we measure it right away, say 2 seconds later, well, that's right, 2 seconds would be right about here. What do you think we're going to get? Well, the binary that we're going to take the measure, here's the probability distribution. It's got all of this is going to be in A prime and just a little bit possibility going to be in A. So if we measure in just 2 seconds and we do a random draw from this binary probability distribution, very highly likely it's going to still be in A prime. And then we measure it again in another 2 seconds. And well, it's going to still be in A prime. And every time we measure it, begins the clock ticking. So we reset the clock. The clock gets reset here. Every time we measure it, it says, okay, measurement, A prime. Now let's start the clock, because that's how the code's written. If, then, if in A prime, then start the clock. So this is just my little simple model of the Zeno paradox. This doesn't apply to any particular system. It's just I'm trying to make this as simple as possible so that the average person can follow what's going on here without being too sciencey. So this is just my simple Zeno paradox system. So that's what's going on. So measurements made to determine the state system A takes a random draw from a binary probability distribution. That's this one. Well, this is tiny. At this point in 2 seconds, this is even not fair. It should be a lot smaller than that, but I couldn't make anything smaller than that you could still see. So that should really be a whole lot smaller. So you get A prime again, you get A prime again. And if I measure it every 2 seconds, I'll always get A prime again. But I may measure it every 2 seconds for 500 seconds. I may measure it every 2 seconds for a day. And every time I'll get A prime. But it's supposed to go back to A double prime in 100 seconds. But you see, it never gets to, because every time I measure it, the clock gets reset. Well, that's a very simple explanation. This clock being reset is a very simple explanation of the Zeno paradox in terms of virtual reality, because I'm just hypothesizing if in state A prime, then start the clock as code. Okay, so it's kind of a simple version of the Zeno paradox. It could be a lot more complicated than that. Could be a whole lot more complicated. It didn't have to, the probability doesn't have to run down like this. It could just go straight across and then bingo, go down like this. It's just a little harder for people to see that. Here, the probability distributions are the same. So that's the Zeno paradox. And you see how a digital perspective of code and an if-then statement makes understanding it trivially simple. Oh, that's easy to understand. Whereas if you try to understand it without the digital, without the virtual reality perspective, it becomes a difficult thing to explain. Much more involved, much more mathematical, much more difficult. But as a digital thing, at least this little simple model I've made, it's an easy thing to understand. So even if this were a lot more complicated and a lot more complex than what I've drawn, still the digital version makes it simple to explain how the Zeno paradox works. Okay. All right. Now, next we go on to the double slit experiment. And because some of you are going to chop off this double slit experiment and make a separate video out of that to send to your friends, I'm going to start with this header card, this header slide, so that everybody will know that this is the third part of a trilogy. The first part, Science, Math, and My Big Toe, is already up on YouTube. The Logic of Virtual Reality is now up on YouTube. And the third part, the logic behind the scenes, details of how and why PMR's rendering engine creates our reality, that's going to be on YouTube right after the logic of virtual reality. Okay, now, in the third section, I go over 3 examples: Schrödinger's cat, Zeno effect, and what we're going to do now is the double slit experiment. So first, I want to do just a short review, because some of you, the things that I said in the first 2 sections are at least hours, if not days and weeks and months past. So let's just zip around and just a few things that I'd like you to remember before we start off on a double slit experiment. First, we're going to jump up to slide 11. Here we go. Now that came from part 1. And I want you to remember that because this is a top-down model and it does not have a deterministic bottom-up calculation, it's a top-down probability model, then when it comes to knowing what's going to happen next, we can't rely on past causality telling us, because this is a top-down probability model. So in a probability model, the question is, how does the computer decide what to render next? In other words, what's the next thing that's going to happen? Okay, well, the answer to that question is it takes a random draw from the probability distribution of the possibilities. This requires the computer to establish and maintain this database, a probability distribution of all the possibilities. Well, we should say all the reasonable possibilities, not all the possibilities. There's some probability threshold where beneath which it does not have to keep track. All right, now, after we said that, I showed you a slide of that probability distribution of the possibilities. And we're going to talk about that when we talk about the double slit. So I just want to refresh you here. This is a probability distribution of the possibilities, and there's 25 different possibilities. Each one has a letter of the alphabet. And how many of these letters we have stacked up tells you how large the probability is of that possibility being actualized. Okay, so you see A only has 1, but K has 25. So what we do is we put 1A in the box off to the right. See that box with the hole in it? We put 1A in there, but we put 25 Ks in there. And we put 21 Ls and 16 Ms and 6 Hs and 2 Xs and 2 Ys and 1 Z. And you see the pattern. So this distribution of the probabilities of the possibilities is how the rendering engine of our reality, of our virtual reality, decides what to do next. So when something new is about to happen, a new measurement is about to be made, then if there are multiple possibilities for the result of that measurement, then the system takes a random draw from the probability distribution of the possibilities. Now, the random draw means that if we put 1A, 2 Bs, 2 Cs, 1 D, no Es, 1 F, 3 Gs, 6 Hs, 12 Is, and so on, if we put all of those into the box, okay, so K has 25, we'll put 25 cards with K written on it in that box. When we're done, there'll be 163 cards in there, each with a letter on them. Okay, 163, that's all the letters that I have here under this curve, from A to Z, all the letters. So then the random draw from this probability distribution means that that box gets shaken and stirred so that all the letters in there are randomized. And then someone reaches in through that hole, picks out one letter, and that is what the system renders as the result of that measurement. Okay. All right. This, I think, was in the toward the end of the first part. I want to look at the middle paragraph right here with physicists try to interpret their analytic approximations to reality in terms of material physical reality. That means they look at the equations and try to come up with some description of what physically is going on, what's physically happening. Well, that creates problems. You end up with things like wave functions collapsing, stretchy space-time that stretches with mass. You end up with fields like electric, magnetic, and electromagnetic, and even morphic fields, any kind of a field. You end up with particles like electrons and other subatomic particles. These things do not exist as physical things. They are models. Okay, physical interpretations of equations become figurative metaphors, not facts. The world functions as if there were wave functions, as if there were fields. You see, the world functions as if there were particles, elementary particles. Okay. That's an important thing to understand. So there really are no wave functions. There really is no wave function that collapses. Space-time isn't really this substance out there that is stretchy, and whenever mass, there's mass, then the mass tends to deform it or stretch it, such that other things slide in, the old bowling ball and the trampoline trick, where you put a bowling ball in the middle of a trampoline, and then if you put tennis balls on the edge of the trampoline, they'll all kind of roll in and eventually go to the bowling ball. Well, that's gravity in Einstein's general theory of relativity. It's just a model. Don't confuse that with facts. Okay. Now, some of the silliness that comes out of that, like I say, is that in Schrödinger's cat paradox, we say the cat's neither dead or alive. It's in a superposition of both states. Well, that's a silly thing to say. That's not really true. And you should remember from Schrödinger's cat, how that worked. Well, we'll just stop by that for a moment and see. With the double slit, we say particles somehow interfere with themselves. Well, whenever you hear a physicist say somehow, you know he really doesn't understand what it is he's talking about. So there are no particles that interfere with themselves. Physicists believe it, or they just call it weird physics. Okay. Now, let's jump one more time to the next one. Okay, this was Schrödinger's cat, and hopefully you recall this. If you haven't, then you need to go back and look at part 1 and part 2 first. But here, I'll just pop over to Schrödinger's cat and show you this again. Okay, what we have done here is a spreadsheet where every one of these rows going across here from left to right, every one of these rows represents an experiment. Okay, we put a cat in a box and did an experiment. And this one, the time in which we made the measurement, we started the experiment at t = 0, and at t = 1 second, we did a measurement to see whether the cat was dead or alive. And the cat turned out to be alive, and the probabilities were that there was 1,395,784 blue balls over here in the box, and only 100 red balls. So that's the ratio of blue to red. So a random draw is almost always going to come up with a blue ball and an alive cat. And of course, we go down here to some other numbers like, here's one that's about, 18. 813 blue balls and only 100 red balls that were in the box. That was the probability if the cat was measured, if we made a measurement of that, whether that cat was dead or alive at 1,620 seconds. That's 27 minutes into the experiment. So we started the experiment, 27 minutes later, we make a measurement. And basically, the random draw, there's 813 blue balls that says alive and only 100 red balls that say dead. But look here, the result was dead. That's because sometimes when you take that random draw, even though there's 8 times as many blue balls as red balls, sometimes it just picks a red ball because there are 100 red balls in there. And even though there's 813 blue ones, this time the random draw picked dead. Now, what's going on here behind this column, this test, I actually do a random draw between what's in that box. I do a random draw with 813 blue balls and 100 red. And this is what the random number generator picked. It picked one of the red balls, dead. So we see, as we scan down here through the various times, that this was Schrödinger's cat. All right, we go down to the very last point, which is 24 hours. And of course, the cat is dead by that time. And you see, as we go up this column, it was mostly dead for these longer times. Here was one where even though there were 100 chances to be alive and 2,276 to be dead, okay, it just happened to grab the alive ball, a blue ball, that time. So had we done the experiment and done that experiment, then this time it would have gotten it alive. But every time we do this, it changes. So if we look at these results, let's redo the calculation, make another random draw, okay? So I can do that here if I can find my computer. I can do that here by pressing F9. That would be right here. There, just did it. See how the dead and alive things change? Again, yes, again, 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 again. So as you see, any random draw is liable to come up with with a red ball or a blue ball. This depends. It's random. But the probabilities up in this area are much more likely to come out with blue balls. The probabilities down here are much more likely to come out with red balls. So anyway, that's how this works. So that is Schrödinger's cat. I just want you to have that in your mind. Next, we're going to go back to slide 24. We're going to start. We've just gone through this short review. We're going to start with the double slit experiment. All right. First, I need to give you a little introduction as to what is the double slit experiment. Why is it important? What's the significance? So somewhere in the early 1900s, and this goes from about 1915, 1910 up through the 1920s into the 1930s, is when quantum mechanics as a science was first established. And it was established because of this double slit experiment. So since this is 2021, I just make a nice little comparison here, because it's been just about a century. Although quantum mechanics wasn't created in a day, like I say, it covers several decades here from around 1910 probably to 1930, But in any case, in 1921, scientists were trying to put reality between a rock and a hard place, to force reality to divulge a few secrets to settle a contradiction. Well, what was that contradiction? The contradiction was that for the previous century, physicists knew about light, about how it refracted, how a prism could spread it into various colors. We knew about how light acted as a wave. If you sent light, coherent light, at a barrier, say a piece of cardboard that had two slits in it, then some of the light would go through one slit, some would go through the other. And each of those slits then acted as a source of light, and you got an interference pattern. And I'll show you how that works just a couple of slides from now. But anyway, that's what waves do. If you do the same thing with water waves, it works the same way. If you have a water wave and a barrier with two holes or two slits in it, the water wave will get to that hole, and from there on, you'll see an interference pattern. Again, it explains the same way as it does with light or any other kind of wave. So that's the wave nature of light. And that was understood for a long time as the science of optics developed. Okay. Now, what happened in the early 1900s was that Einstein, studying the photoelectric effect, for which he got a Nobel Prize, by the way, he discovered that light seemed to be a particle. It had little chunks of discrete momenta. Okay, so it came in particles. So now we had a contradiction. Because if you take a background, the piece of cardboard with two slits in it, and you throw particles at it, then particles won't create a diffraction pattern. I mean, they won't create an interference pattern. The light diffracts through the slits. Sometimes it's called a diffraction pattern, but I'll try to remember to use the term interference pattern. So particles aren't going to do that. Particles will either go through one slit or they'll go through the other slit. They can't go through both. It'll go through one or the other, and then it'll hit the screen right behind that slit. So you should get two piles of particles on the screen, which is behind the barrier with the two slits in it. One pile behind one slit, the other pile behind the other slit, because we know particles travel in a straight line unless acted on by some external force. That was one of Newton's laws. So now we had this contradiction. And the contradiction was troublesome because we also knew that light particles, we call those photons, are independent of each other. They don't interact with each other. So if you have one photon by itself and you have a photon in a crowd, say with millions of other photons, doesn't make any difference. Each photon acts as though it is the only photon there. They're non-interactive. So a bunch of photons should act exactly the same way one photon acts. Being in a crowd makes no difference. So if you have like a laser pointer, well, there's literally billions of photons that make that little red spot on the screen when you point the laser pointer. But each one of them in that beam, it's just as if it were all by itself. It does not interact with any of the others. So in that case, what's going to happen when we send photons one at a time at the double slits? Well, if they're particles, like Einstein said, they should pile up behind each slit. If light's a wave, then they should make an interference pattern. So eventually, in the early 1920s, some bright scientists figured out how to do that experiment. And that was called the double slit experiment. And what happened was that if nobody knew which slit the individual photons went through, then those photons, after going through one or the other slits, would distribute themselves on the screen in an interference pattern. And that was surprising because these particles were moving around and making a interference distribution when there was nothing to interfere. There's just a single particle, nothing to interfere with. And they should not be able to do anything but go in a straight line. But they violated those ideas and distributed themselves into an interference pattern. But as soon as the scientists put a little photon detector at each slit to see which slit the particle went through, the photon went through, then the photons all pile up in a pile behind each slit. So you had two piles, one behind each slit. They acted like particles. So that was the contradiction. Okay. If you didn't have the which way data, which means which slit did it go through, which way did it go? If you didn't have any which way data, you got an interference pattern. If you did have which way data, you got a particle pattern. So that's what happened. And that's the beginning of quantum physics. Well, that's, quantum physics didn't start on a dime either. So that's part of the beginning of quantum physics. Okay, so could reality have responded in some other way that made more sense? And the answer to that is no. We will show that reality, consciousness, the rendering engine of this virtual reality, could not have done it any other way. It was constrained. Every other choice would have forced it to violate its own rules, would have forced a contradiction. Okay, so it did what it had to do. Now, will all become clear and simple and logical with the right perspective? Yes. If you have the right perspective, all of this will make perfect sense. It won't be so mysterious. Scientists made up a term called the principle of complementarity, which said sometimes it acts like a wave, sometimes it acts like a particle. It just depends what you're doing. And of course, though that's true, that's not really very helpful. It's not that sometimes it acts one way and sometimes it acts the other. It's very consistent how the consciousness system, how the computer that computes our virtual reality, how the fundamental substrate on which all reality is constructed, it works the same way all the time. It's just sometimes it looks like it's a wave, remember, as if it were a wave, and other times it looks like a particle, as if it were a particle, when in reality, it's neither one. It's virtual. It's not actually a physical wave of any sort. It's not a physical particle of any sort. It's all virtual. It's the way we compute. All right. Well, that secret that reality divulged in this experiment was a much bigger secret than we knew how to understand. The next century, which brings us right up to 2021, a century later, scientists are still scratching their head about that, you know, that weird science, quantum mechanics, quantum physics. Just nobody will ever understand it. That's a quote from Richard Feynman. Nobody will ever understand it. It kind of gave up on trying to figure out that perspective in which it would make sense and just accepted it as beyond our understanding. Well, as I mentioned earlier in these talks, all big breakthroughs, all big paradigm shifts, you know, from flat Earth to round Earth, from Earth, the center of the universe, to Earth, just a planet going around, you know, a star in a solar system. All of these big ideas occurred because of major viewpoint changes, paradigm shifts, perspectives changed. That's all it takes. You just have to see reality from a different perspective, and then the truth makes sense. All right. So the last point here is that in 2021, a century later, it turns that in order to get it, to understand it, one has to let go of materialism and determinism and realize that consciousness is the only thing that is fundamental, that consciousness is the substrate from which and upon which everything else is constructed, and that we live in a virtual reality created and run by and for consciousness. After absorbing that, everything gets both simple and elegant. All right, let's start looking at the double slit experiment. On the left, I'll explain this from left to right. On the left, the first thing we see here is the particle generator. Okay, now these little schematics I'm putting together, these little cartoons, are basically to illustrate the concepts. Okay, this is not really showing you, the actual equipment to do it. The actual equipment to do it is a lot more complicated than this, but just conceptually, this is how it works. Okay, this is going to be our particle generator. It's just something that throws out, well, in this case, we'll talk about photons, but maybe it throws out electrons or buckyballs or any sort of thing. It's just a particle generator. Okay. Now, this particle generator can be turned up so that it throws out millions of particles, okay, a beam of particles. And it can be turned down so that it just sets out one particle, just spits out one particle at a time. Okay, so it's adjustable as to how many particles are going out per unit time. And this is the little end cap that sits right on the end of this tube so that the particles that it generates have to come out through this little rectangular hole. Okay, and we'll talk more about that later. All right, now here are the double slits. Slit 1, slit 2. Here are two detectors, detector 1, detector 2. Now, this is a photon detector, and if a photon goes through, or a particle detector, but if we're talking about light, we'll say it's a photon detector. And if a particle goes through slit 1, this makes a detection. It says, got a particle, just went through 1. And this is a recorder. It records the fact that it was slit 1. In other words, X, this is X axis down here going this way. So it occurs at this X and the time, T. Okay, so we know the time that the particle went through it and that it went through slit 1. And same over here. If a particle goes through slit 2, this detector detects it and it records that particle went through that slit at this time. Okay, now right here we have them all turned on. So detectors are detecting and will detect any particle that goes through the slits, and the recorders are recording and they will record that information. Okay. Now over here is what we call the result screen. So the particles go through these slits and hit the screen. Now, because we are collecting which way data here, because we have D1 and D2 turned on and R1 and R2 turned on, so we're collecting, we're detecting and recording which way data, then, as I said earlier, the particles will just pile up behind each slit. So here's a pile of particles that have gone through slit 2. Here's a pile of particles that have gone through slit 1. Now, I know you're thinking from this picture that there's something wrong here, because we talk about this particle generator having it's a 50-50 chance whether the particle goes through 1 or 2. And we don't know which one it's going to go through, but it's going to go through one of those. And you're thinking, well, it looks like right now it's going to hit the space in between them. That's where the little red dots go. It's going to hit the space between them. And how come? If you aimed it right, they'd all go through 1. Or you aimed it over here, they'd all go through 2. Or if you aimed it where it's aimed, they're all going to hit the middle. So how is it that we have particles that have a 50-50 chance of going through either slit? And how come that they could go through slit with a Y, which is up this direction? See, here's Y going up this direction. Why could they go through here at the bottom of the slit and at the top of the slit with equal probability? Looks like you'd have to move this thing up and down to get them to go through higher or lower parts of the slit. Well, that's just the way we've drawn it here. Now I'm going to show you how that works and why we have an equal probability of going through either slit, and why the probability in the Y direction, which is the top of the slit to the bottom of the slit, is also all has the same probability. It doesn't look like it from my cartoon here, but I will show how that works. So you'll just have to trust me at this point that the probability of a particle going through one slit or the other is equal. It's equal probability to go through 1 as it is to go through 2, and that it can go through any Y value, top of the slit to the bottom of the slit, or anywhere in between, with equal probability. So that's why over here on the screen, we have these little piled up particles that kind of look just like these slits. You got 2 slits and 2 stripes of particles. All right, now over here we have another detector, D3, which detects anytime something hits a screen. It has an X value going down this way, and it has a Y value going up this way. So, and it has a time. So every time some particle hits this screen, D3 detects it and then stores its X coordinate, its Y coordinate, and its time coordinate. And we have this turned on. All right, so that's how the double slit works. Now, we said that when you make a measurement, you're taking a random draw from a probability distribution. Well, these are the probability distributions here. And they look sort of like these slits. All these things look like two slits here. They look similar. That's because these probability distributions are very narrow in X. Okay, so take a random draw from this probability distribution to see where the particle hits the screen. So that's how a particle actually gets put on the screen. Right? You can't see these particles. These particles are invisible. They're little photons. So you have one of them coming out at a time. You get a detection and a time. just a little bit later, and we can compute just how much later that would be. It's the time it takes a light to go from the double slit to the screen. That much later, we get a particle on the result screen somewhere. And here's the X, the Y, and at the time. So we can correlate the time here with the time here and know, that particle came through this time. It must have, and we found that particle at just that little bit of time earlier in R2, so we know it came through slit 2. See, so we compare the time here with the time here in order to know exactly which slit each one of these particles came through. That's our which way data. And these particles got here because every time we fired a particle, we don't know where it's going to land, as a measurement is taken at the result screen. That's where the particle actually lands and gets measured. Where did it hit the screen? That's the measurement. And we take a random draw from this probability distribution, and that's where we put the particle. Okay. All right. Now, this is kind of abstraction here, the way I've drawn it, because we're kind of looking on a side angle, about 45-degree angle. If we look straight at it, it really looks like this. That pile of particles aren't in a line. They're not all right on this center line. Some of them get over here, some of them get over there, but they're mostly a big pile here, right behind the slit. So the slit was right here. All right. Now, by the way, I've taken these slides from another briefing that I did back in 2016. I went over all of this back in 2016 in LA. You can find that if you go on YouTube and do a search for MBT 2016-LA or MBT LA-2016. I think that's the way it was, MBT LA-2016. And you'll find these slides there. I've just pulled them out and used them, some of them, to explain these to you. So I'm not necessarily going to explain every detail on the slide. For this purpose of explaining this to you, I don't have to talk about all of it. This is the standard double slit experiment, and we see the which way information gets collected here, and therefore we get the no interference pattern, just piles of particles that look sort of like this if we looked end on. All right. Next. Okay, now we're going to look at it with the detectors turned off. And if you turn the detectors off, it doesn't really matter whether the recorders are on or off, because there's nothing to record. There are no signals get to the recorders. So whether the recorder is off or the recorder is on makes no difference. There's nothing to record. So we've just turned these detectors off. That means there is no which way information. Okay. If there is no which way information, then it works a little differently. Okay. We have the particle generator. It spits out a single particle with an equal probability that it could go through either slit and an equal probability of where it goes through that slit from top to bottom. And what happens now is instead of two piles of particles, we get an interference pattern. Now, I don't know if you can see this very well, but most of the particles land here in the center, and that's darker. The particle density, or the dot density, is a little smaller here. That's the next peak. The dot density smaller yet, it's the next peak, and the dot density smaller yet. So it's like that. We've got more dots in the middle and fewer dots in the lines as we go out. And the diffraction pattern, or interference pattern, probability distribution, looks like this. So this is probability versus X direction. Well, this is the greatest probability. That's why most of the particles end up here. The next greatest probability would be over on this side and that side, which is this line and that line, and they both have the same density, and so on. Okay, so the way each point got on the screen was that a random draw was taken from this probability distribution. Well, where did that probability distribution come from? Well, here's where it comes from. First of all, I remember earlier, I think it was probably in section 2 of this trilogy, I talked about how our reality was a probability distribution sitting on top of a mostly deterministic rule set. Okay, and that rule set, mostly deterministic rule set, which had some randomness in it, but it was mostly deterministic. That rule set could create the probability distributions that the higher level things needed, the up in the macro world. It could produce those probability distributions very accurately, or as accurately as it needed to. Okay, well, here's what happened when the physicists set up this experiment. For the first time, or any time physicists set up an experiment like this, of course, it gets set up in a virtual reality. This is a virtual reality. So the people setting it up are avatars in a virtual reality. They use virtual computers. They put them on virtual tables. They have virtual laser particle generators. Everything has to be created in this virtual reality. So the virtual reality is aware of all the piece parts, where those piece parts came from, where the ore came from that was smelted and refined into steel that was part of the table legs. The system knows where, it knows everything about everything, if you will, because it's been rendering this virtual reality from the beginning. So since it's the renderer, it has all the information. Now, the larger consciousness system, or what we call the virtual reality rendering engine up here, upper left corner, let's say, let it run 437 particles. Okay, so the larger consciousness system, the VRRE, runs 437 particles through this experiment's logic. In other words, everything in this experiment has logic, things that it does. What does it do? Well, the logic of the particle generator is it makes particles, and you can turn up how many particles per second it makes. Okay, the detector has the logic of it can tell when something goes through the slit. The recorder has the logic in it that it will remember whatever was detected. So every piece has its own logic, and if you take all the logic of all the pieces and put it together, you have the logic of the experiment. Okay, so the larger consciousness system takes 437 particles and runs them through this experiment's logic to generate the distribution that you're going to see on the next slide. Now, it needs to do that because every implementation of this is going to be slightly different. These distributions are going to be a little fatter or a little more smeared together and not quite as much. All these between peaks goes all the way down to zero, and it may not go all the way to zero. There may be, things just look lumpy. So they're all different depending on the equipment and how it's put together. So whenever a new one's set up, the system has to go do a little experiment down at the rule set level. Right? It has to model this because virtual reality is a modeled reality. It models this experiment, and what it does is it produces this. Okay, when it runs particles through there, this is what it sees. This is what it creates. So here's the 437 particles. Here's the probability distribution that it got. And we're going to tell you in a little bit later why it got this, why it had to get this probability distribution, or why this was the distribution that it got. All right, now this is just like the distribution I showed you before. See all these little numbers? There's 2 in this box, and 5 in this box, and 5, and 14, and 10, and up here, I think it says something like, I don't know, I can't read that little number, maybe 25 or something. Up here it says 52. You'll have to get really close to read these tiny little numbers. But so these are the probabilities. The taller it is, the more probability there is. So now you put all of these things in a box, right? Now we have a box, and we're going to put, now if this one says 14 here and this X value, so you're going to put 14 little cards in there with this X value on it, right? Just like we did before. This one says 52. We're going to put 52 with this X value, this X value. These are the X values, all the little values of X as we go across here. So this X value, it's just the normal X axis. So X gets bigger as you go this way. So whatever the X is right at this spot, we're going to put that number for that X in 52 times in the box, just like we did before. And we're going to do that for all these various values of X. And then as we do this experiment that we were just looking at, that's this distribution. And we're going to randomly reach into that box and pull out a piece of paper. Every time a particle gets shot out of here, goes through one of the slits, hits the screen. Where is it going to hit the screen? Well, take the random draw from that probability distribution, and that's where you put the particle on the screen. And if you watch this happen, if you would be watching this experiment, you wouldn't just instantly see all of these dots. You'd see that a dot over here, then a dot down there, then a dot up here, then a dot over here. They just come in randomly because that's the random draw from that distribution. But eventually, after enough particles go through, because there's more pieces of paper, because there were 52, in this peak, more X values that are right in this part of the X axis, right under this column. There's more pieces of paper with that X in it because those were taller peaks. So you're going to get more dots there. So eventually, after enough particles come through, you get this pattern. Okay, this is the interference pattern. But it comes out one dot at a time, and that dot doesn't like do all these, then do all those, and do all that one. That dot just randomly occurs someplace. And only after thousands of dots would you see this nice pattern coming out like that. All right. So now here's why the system used this probability distribution, because you see, that's the answer. Why did those single particles end up on the screen in a pattern like this? Well, because the probability distribution that was used, the probability distribution of the possibilities looked like that. That's why it came out that way. So why did it have to look like that? All right. As we said, photons are completely independent particles. I'm going to have to grab this thing and pull that down a little bit so that we can see it. Okay. So that creates a consistency problem. Now, this virtual reality has several constraints. It just can't do anything at once. It has to create a virtual reality that does not have conflicts in it. It doesn't have, what can we say, things that don't belong. It has to do two things. One, it has to always abide by the rule set. It cannot create anything in the virtual reality that is not in consonance with the rule set. The rule set defines what can happen in the virtual reality. So that's one major constraint. The other constraint is it has to not create any conflicts within the reality, any inconsistencies. It wants the virtual reality to be a good virtual reality, and a good virtual reality is one where you can't tell it's virtual. If it's really, really a good virtual reality, then nobody can tell it's virtual. It's so real. That's a good virtual reality. So it doesn't want to create any inconsistencies well, I should say no objective inconsistencies, and it has to abide by the rule set. All right, now look, here is the problem. Let's first look at light as a wave. When light's a wave, I'm going to show you why it ends up in this interference pattern. These lines represent a plane wave. That means all the phases are the same along this line. That wave, you can think of it as a laser pointer with a big spot. The spot's going to cover up both these slits. So the red spot from the laser pointer is going to cover up both slits. So that's a plane wave, and it gets to this, and these are barriers, 2 holes. That's a slit in the barrier. We're looking just down from the top. Now what happens is, notice, these turn into sources. This little hole, some of the light goes through here, some of the light goes through there, and that makes a little source of light, and that's a little source of light. As these sources spread out, you see they interact, they overlap. Now, notice that D1's a shorter line than D2. Said that wrong. So there's a difference. Now, if the difference between D1 and D2 is always 1 wavelength or 2 wavelengths or 3 wavelengths or any integer number of wavelengths, then what happens is that here you have a wave. It's not exactly a sine wave, but I was a little limited here in PowerPoint, but pretend that's a sine wave. And a wavelength goes from the beginning here to the beginning of the next one, or it could go from the top of this one to the top of the next one, or the bottom of this one to the bottom of the next one. That's just 1 wavelength. Okay. Now, if there's 2 waves, here's a red one and a black one, and the red one is just 1 wavelength out of phase with the black one. So that when this red one is ready to start over, well, that's where the black one starts. So the 2 of them run together like this. You have one here, and then you have one that matches it in phase. Peaks are under each other, dips are under each other. Well, when that happens, the 2 add together. 2 peaks makes a peak that's double sized. 2 dips make a dip that's double sized. Okay. Now that's what happens in all these black dots. Here, because this slit and this slit are both equidistant from the thing in the center, it's both D1 and D2 are the same here, well, then they're in phase. So we get a spot of light. Funny that a spot of light is made black, but oh well, so much for artistic license. So here's a spot of light because D1 and D2 are the same. The distance from this slit to that middle point and this slit, that middle point. So they're in phase, like this. Now, between these points, the distance between D1 and D2 is some odd integer number of half wavelengths. In other words, it's 1/2 a wavelength, or 3/2 of a wavelength, or 5/2 of a wavelength. Okay, so then you have this case, where now you have just half a wavelength. See this out of phase thing I'm talking about? You have 1/2 of a wavelength is over, and then the black one starts. So now the black one starts like this, and the red one keeps on going, and you see they're out of phase. You have a dip occurring at a peak, and then the red peak occurs to the black dip, and vice versa. They cancel. So when you add those 2 waves together, you get nothing. There's no light here. That's why there's no black spot. So that's why you get a peak like this. Your interference pattern is you get light that comes to here, some comes to here, some comes to here, and so on. And in between, you don't get any. So if this is like that graph of how much light do you get here? Well, we get a little bit, so it's a small peak. You get most of your light here. That's a bigger peak, and so on. So this becomes the pattern. That's what the physicists see. They see more photons hit here, which is this bigger peak in the middle, and then nothing in between, and then more than photons hit here, but not quite as many. That's the second Okay, that's the double slit. Now, the problem that reality had was, of course, particles are supposed to go in straight lines, but if they do, there's going to be an inconsistency in the reality because the particles don't interact with each other. And whether you have a few particles or only one particle, you have to get the same result. Well, we already knew what a lot of particles would do. That was optics. That's the wave. That's just, this wave is just a whole lot of little photons, lots of them. And they make this kind of an interference pattern. Well, little single photons really aren't any different than a whole lot of little single photons because they're not interactive. So they also have to make this pattern. So you see the system was backed into a corner and it had to produce this kind of a distribution for the single particles in order to maintain a consistent virtual reality. So it did, rather than have an inconsistency in the virtual reality, have the virtual reality illogical. You see, now this is surprising, but it's not illogical. So that's why the system, as we said here, it got this interference pattern and said, all right, that's our probability distribution. Now let's go up here and take random draws from it, and that's what we'll put on the screen. All right, so that's why this particular result occurred. Reality had no other choice. All right, now we've already seen this, this slide. And here you see the Y value and see all the probabilities are the same. They don't go up and down. Every Y has the exact same probability. So that's why it doesn't matter about Y. We don't have to care too much about Y. Now, I'm going to show you a little bit about these probability distributions. All probability distributions aren't going to look like this. That's just the probability distribution for an interference pattern. Sometimes the probability is a binary. A binary probability distribution is like this. Okay, of all these X values, there's 0 in all these other X values except this one, X17, and zeros on all these until this one, I think that's X26. If you get these slides, you'll be able to blow them up and see those little tiny numbers. Okay, so the probability is equal. Could just as easily get one as the other. Okay, so this is the distribution for that. Now, what are we going to use this for? We're going to get this to decide what slit it goes through. That's a measurement. That's a choice. Every choice, the system has to know what to do. So the gun fires, right? Now we're on a jet. Let's jump back up here to the first slide. The gun fires. Now, what slit is it going to go to? Well, the system doesn't have any way of knowing that, so it comes over here and does a random draw from this probability distribution. This is this is one of those that has just two choices, which means when you take a random draw, you're going to either get a 1 or a 2. This is a box that has n pieces of paper in it that say this X value, X17, and exactly the same number, n number of pieces of paper in it that has this X value in it, X26. And you reach in and you shake that box up and you reach in, you pull one out, and you're going to get either a X17 or you're going to get an X26. Now, you're thinking, what is X17? Well, I just numbered them. I just numbered, 0, 1, 2, 3, 4, 5, and this just happened to be 17. So I'm just calling that's the X value. And I kept on numbering, and this one was 26. So those numbers are just randomly placed there. So it's an equal probability, and you're not going to get any other number because the box doesn't have anything in it except x17s and x26s, and it has an equal number of those. So that's called a binary probability distribution. So up here, the first thing, a random draw from a binary probability distribution, and it came out x2, this one, x26. So it comes over here at x26 and says the particle goes through this one. See, there really is no particle. See the point? There is no particle. There's just modeling the particle. So then it made it, the particle will go through here. Well, if it goes through here and there is which way data, then it draws from this and it gets a pile of particles here in a line. And here, first thing it does is that draw from a binary distribution, decides which slit it goes through, and then it comes through here and does a random draw from this distribution. You see? So every time a measurement is made, like what slit does it go through, or where does the particle hit the screen, that's a measurement being made. Every time a measurement's made, the system takes a random draw from a probability distribution of the possibilities, and that's the answer. All right. So let's move on now and actually see how this is done. Okay, remember that little end cap I was talking about? Remember there's off to the left here, off the screen is where the particle generator is. And this is just the very end of where the particles come out. But I made it real big so we could see what's going on here in the detail. So you notice that here, it's all red. This is a laser pointer saying it's a red light. It's a red light laser. And here's where the slits are. These are the slits. So what you do is you turn this particle source laser light intensity up until you have a beam of light, not just a single particle. And you look at that beam until you have a uniform density of particles inside the dashed red line. Okay, here's the dashed red line going around here. Just goes around the slits, and you can see that it's kind of reddish there. So we have a uniform density of particles inside the red line. And we fit the line as tightly as we can to the slits. All right. So that is now the beam, because it's making lots of particles. Now, when we turn that down and it makes just a single particle, well, that single particle could be created anywhere inside this box. It could come anywhere. It's an equal probability because the light density is the same everywhere. That means it's an equal probability that a photon coming out of this end cap has an equal probability of hitting anywhere inside the dotted line. So that's how you get the probability is equal that it could go through slit 1 or slit 2. It's because you actually have a source that covers both of them equally with equal density. Okay. So, and also you see that it covers from bottom to top equally. So it doesn't matter. It's equally to go through with a Y here or with a Y here or here or here. If it goes through slit 2, it's all the same. Okay, so that's how that is done. Well, I should say one more thing. Notice there is little bits of pink, little bits of light that get outside of this. And we have light that's here covering the slit. So particles do hit outside the slits here and here in between the slits and here. They do. But we don't care because enough particles will go through one slit or the other. And when they do, they're part of our experiment. And when they don't, and they hit between the slits or they hit out here, they're not part of our experiment. All we do is look at the particles that go through the slits. You see, so now it's all probability. A particle comes out of here, there's a certain probability that it's going to land out here on the edge and not go through a slit. It's going to land in the middle, going to land out here underneath. there's some probability that it could land equally anywhere in here. So now we look at, what shall I say? Well, we're not quite there. So we're going to look at the probability of how that works. We'll see that a little later. So here we are now, putting the particle on the screen at the detector R3. Okay, so here is the probability distribution. Right, here's the 1,608. A particle comes out. A random draw is taken out of this distribution, puts it somewhere here in X. A random draw is taken out of this distribution, puts it somewhere here in Y, and there's where the dot is. It just puts the dot there. Okay. So I hope that's easy enough to get. Okay, let's go down to the next one. Now we're going to look a little bit more about this particle generator, because the system has to model this particle generator too. And now we're going to model it. This is a little probability distribution of the delta t, which is the time between consecutively generated particles. Okay, time between consecutively generated particles. Now, sometime, see, here's all the possibilities. Sometime that time may be real short. Here's delta t going this way on the axis. So sometimes they're real short here. Sometimes they're real long out here, big delta t, little delta t, but most of the time they're somewhere in the middle. Okay, so it's just the probability distribution of the delta t's. This is how the rendering engine models the particle generator. So if that's the case, then we have two things we have to keep track of here. One is the probability of time between consecutive generated particles. The second is this frequency, which is an average frequency of particle generation in particles per second. So we're going to get, here's an example. Okay, here's an example. If the average number of particles per second is 30 particles per second, PPS, then the delta t is 1/30th of a second. See, delta t, and this is delta t, the little bar means average. Up here, I drew the bar over the word average. That's what the bar means. So the average delta t then would be 1/30th of a second. And we'd have 30 particles per second. So if you have delta t, you have the frequency of how many particles come out per second. Those two go together. And the way you get delta t is you come in here and make a random draw from this distribution. You see? All right, so we'll go down one more. Now, here's that distribution. And you see, these are probabilities now. Probabilities going up this axis. This is delta t in milliseconds. So here, the probability of getting 5.55 milliseconds is just 10. So there's 10 pieces of paper with 5.55 milliseconds written on it. There's 10 pieces of paper with 11.11 milliseconds written on it. But there's 20 pieces of paper with 16.66 milliseconds, and so on. So here we have 90 pieces of paper with 33.33 milliseconds, and so on. So another 30, another 20, 20, 10, 10. So we take all these pieces of paper, which turns out to be a total of 270 pieces of paper, put them in a box, shake them up, pull out one on a random draw, and bingo, that is the delta t. That gives us the frequency. Okay, so now we know when the particle's coming out. So now we've modeled this whole particle generator. We don't have to model the insides of it. We don't have to model the gas where the atoms get pumped up into higher states and then they come back down and create light as the electrons fall into lower orbits and so on. You see, that's modeling it from the bottom up. That's modeling all the little details. We're modeling it statistically. So we can model that whole process, that whole complex process of that particle generator just by this curve. We take a random draw and that's when the next particle comes out. You see, but we can only do that because we've generated this curve by looking at the details of the rule set. Remember, deterministic rule set at the bottom, probabilistic on top. Okay, so I just made up some notional numbers here and said, well, this is the red dotted line. These are the two slits. It says it looks like about 6 slit areas fill up the box. So you can run through this if you like. It's not really important. And you can see about how this works out. Basically, you get about 4 particles per second through each slit if we let it be this average value of 33.33. Just playing with the numbers a bit, not really too important. All right, so now we're ready to do a double slit experiment. The double slit experiment is now reduced to 5 random draws for each virtual particle. Remember, this is a virtual particle generator being constructed by an avatar in a virtual reality. All of it is being created virtually, but it has certain logic to it. All right, and the results have to follow that logic. So here's what reality does. This is what the rendering engine does. It doesn't have to worry about atoms in their excited states, electrons coming down to lower orbits. All of that stuff actually doesn't exist. Doesn't happen that way. Electrons are not really in little orbits zinging around and then drop down orbits. They just change energy states. See? So it just models this whole thing as this. Plus, if you have a massy particle like a buckyball or an electron, then you also have to model the velocity of the particle. If we have photons, we know what the velocity is. It's the speed of light. It only comes in one velocity, and that's the speed of light. So we don't need this then. This would be unnecessary. But if we had an electron or a buckyball or anything else, we'd need to also do a random draw from a probability distribution of the velocity. So the velocity could be as small as this, could be as big as that, but most of the time it's here in the middle, and you take random draws out of that. So here's how the double slit experiment works behind the curtain where you can't see it. It's a probabilistic version. Forget all the atoms and elementary particles and all the rest of it. First question is, when does the particle arrive? Right? You have a generator. When is the particle going to get to the slits? That's the first thing we need to know. Well, first random draw is from this distribution, and that'll tell us when the next particle is coming out. It's coming out delta t after the last particle came out. Okay. Secondly, you take a random draw from this probability distribution of p velocity, probability of velocity. How fast is that particle going? Takes a random draw, and it gets that number. Next, it has to answer the question, what slit does it go through? Which recorder does it write on? It takes a random draw from this binary distribution, and it's going to pick a 1 or a 2 because those are the only choices in the box. And that's the slit it goes through. See? And we know how often that's going to happen. When we put the numbers in, those numbers said there's going to be about 4 particles per second going through each slit. So it's got all the statistics that goes with that. So every particle, again, doesn't go through the slits, but we know that on the average, about 4 particles per second are going to go through these slits because that came out of this P sub delta T PG, that's delta T particle generator, came out of here. All right. So when it does this random draw, it says do a random draw here, I got a 1. All right, then the particle went through slit 1, and I'm going to write the result here at R1. And I do again another random draw, I may get another 1. Next particle may go through 1 too, and then keep going. And eventually all this data will fill up, and as you fill up that data, this data now is available to a player, right, to a consciousness. Why is that important? You know, we have this thing about the measurement problem and the observer paradox. Well, remember, the virtual reality only exists in the minds of the players. If the player doesn't get the data, it can't be in the virtual reality. The virtual reality only exists in the minds of the players. That's why the observer is so important. Because if there is no observer, then nothing can change inside the virtual reality. So here's the first data that an observer, a player, can see. All the rest of this just happens, right? The physicists just sit in a room and they don't know what's going on inside this thing. You know, they've just known that the logic that they've put together produces particles and that they can turn it up and turn it down. The logic, their physics, what they understand of the rule set, let's design this. But then they just turn it on and it works. Well, all that detail is not being computed. That takes too much time. It's too hard to do. All that's being computed is, you know, random draw, random draw, random draw. And that gets us data, gets us a detection and data. Okay, because it knows the timing. It knows once the timing here between the particles. It knows this distance, so it knows how long it takes to get here. It knows the distance of these wires. It knows how long that takes. Because all of this is set up in a virtual reality. It actually is creating all of this. Okay, it knows the distance between the slits and the screen, so it knows how much time to take the particle to get there. So it knows those things. All right. Now, the fourth random draw it takes is from P sub x. It says, all right, we got a particle. It went through this slit from random draw here, went through the slit. It has a certain delta t, so we know when it's going to arrive here to the screen. It has certain velocity. Also lets us know when it's going to arrive here at the screen. So where does it impact the screen? Where does it hit the screen? Well, it goes in and it takes a random draw from P sub x. Right? In this case, we've got which way data. So it's going to just take one of these two little skinny distributions that really look like that. And then it says that's the x value. So it comes in here, random draw, pulls out an x value. Says, there's where it hits on the screen, right there. Then it says, well, what's its y value? And it goes over here and says, well, all the y values are the same. Any y value would do, so it takes a random draw from this, picks y value. That's where it puts it on the screen. Okay, so that's it. That's how the double slit is done at the probability level. You see, all of the world that we live in, even if it has to do with atoms being pushed up in higher energy states and crashing back down in emitting light, we don't have to calculate any of that. That's the beauty of this being a probabilistic reality. It has to be a probabilistic reality. It's just too hard to calculate everything from elementary particles up. It takes too long. There's too much to do, and it's a waste of time. Any intelligent computer scientist would just use that rule set to generate the probability distributions it needed in order to turn this whole experiment into 5 random draws. You see the efficiency in this, kind of the beauty in this is that you get to do this very complicated experiment, and all the virtual reality rendering engine has to do is take 5 random draws. Well, how long does that take? A nanosecond a piece? Not really, because that computer that is our rendering engine runs a whole lot faster than our computers. In our computers, it would be a nanosecond apiece. But for it, it's probably a nanosecond apiece. So that's how efficient this is when you let everything above the rule set be probability, and you have that rule set to generate the functions, and that rule set knows everything because the rendering engine has rendered everything that's physical. It's a virtual reality. Everything in this reality, including the iron ore that was the steel in that table leg. All right, now we drop down to the next one. Okay, this one that we just was when we have this which way data and we get these two. Now we're going to go down to the next one, which is no which way information. Okay, when you have no which way information, we don't know what slit it goes through. Doesn't matter. It's just going to go through slits. So we don't have a binary up here. We don't have that random draw. So there's one random draw we don't have to make. But we still need to know when it's going to arrive at the screen. So we still need to know how long before the next particle comes out and how fast is it going. Okay, so we still have to make those two random draws. Then the third draw, we come over here, take a random draw from the interference pattern, and that's where we put our particle. It turns out to be, it looks like this. Okay, and then of course there's a random draw from this. It's not even necessary to do it. You just randomly put something in Y. Each time you draw an X, you just put it in at a random Y. So now we have one less random draw because we don't care about specifying what slit it goes through. It doesn't matter. You see, it doesn't have to go through a slit. These are virtual slits. These are virtual particles. The particle doesn't have to go through a slit. It's just you have to know when it's going to arrive, and you have to make this draw so you know where to put what X and Y coordinate. You put it when it's supposed to arrive there. So that exactly the time it's supposed to arrive, you put a dot at the X you get out of this random draw and the Y you get out of that one. That's how the double slit experiment works. All right. Now, that's kind of the end. So I have a couple of more slides that you will get when you get all the slides. I have a couple of others I'll show you, but this basically tells you that if you look behind the curtain at how our reality is being rendered, it's rendered very simply. You can follow quantum mechanics just by following the logic and looking at time always moves forward. And you can just look at what probability distributions are required, have to be there in order to be consistent. And if you do that, you can look at the delayed eraser, you can look at any of the experiments, and you can say, well, okay, here's the logic of the experiments, here are the distributions that are required, and here's the result. So now quantum mechanics becomes reduced to a simple probabilistic rendering. We don't have wave functions. We don't have collapses. We don't have any of that. So it's a very efficient process of rendering this virtual reality. It's not what people think. They think that it's going to be the bottom-up approach, and these calculations are horrendous, and what computer could possibly do all of that? Well, it doesn't have to do all that. All right, now here, this last slide was just to ease your confusion. When you're doing show and tell, you provide that distribution this way. There's a bunch of little dots going up and down in the shape of a slit because that's easier for people to understand with nothing actually between them. It's just empty space between each bar. In actuality, when you do the physics in the lab, what you get is something like this. This is basically the probability distribution And that's the way your graph will actually come out in the lab. This is a way of presenting it. Makes it a little easier to deal with. And that's if you have a interference pattern. If you just have a particle pattern, it's the same thing. This is what it looks like in a lab. This is what we put out for people to see. It's kind of a cartoon that is easier to understand. And this is what these look like. This is what these look like if you looked at it head on. Now here, notice here's I showed kind of the optimum position here for setting this up is that here's the center peak and the peak on either side, and here's the slits. It's nice if you can set this up with the slits. Just fall in these dips. I would be here and here. They just fall in the dips between those two. That's the way that we'd like to set up our experiment. And you can do that by setting up, just because how far apart these peaks are and so on has to do with how wide is the slit, what's the wavelength, how far away is the screen, that sort of thing. So those can be adjusted. Now, the last thing that's going to be in your packet of information, if you get the slides, is a definition of information. That's kind of a key thing, but I'm not going to go over that. If you get the slides, this will be at the end of it, because it's, I just put it all on one slide. That's why it's such a small font. I don't really want to talk about it, but it's here. As part of the package, if you get all the slides, you'll have a more detailed explanation of exactly what do we mean by information, because we use that word a lot. All right, that puts us where we are. We've done number 3 now completely. We've looked at logic behind the scenes, details of how and why PMR's rendering energy creates our reality. And we've gone through 3 examples. Now, hopefully you've seen in these examples how reality is actually rendered and how much simpler it is than how reality is computed. If you're understanding how it's rendered, then you will understand how it works. Why it's rendered that way tells you how it works. So that's really what I wanted to show you. You know, behind the scenes is a lot simpler than you think. It's a probabilistic model. So why should particles be probability distributions? You know, that's the big secret, right? That's the big problem in quantum physics. Why should particles be best modeled as probability distributions? Well, the answer to that is because our reality is generated at the probability level. Top-down probability can't be rendered any other way efficiently. Trying to render it up from the bottom up with particles and all that calculation is just intractable and nonsense. It doesn't work well. This is so much more efficient and works so much better. And remember, we have this database that I talked to you about up in part 2, the database of everything that could possibly happen and the probability that it would happen. Okay, I call that the future probable database. And it's not everything possible, but it's everything possible above a certain threshold of probability. We discussed that earlier. If you would like to go back and do that, you should do that. You should, you know, if you want to look at more detail, just go back to the part 1 and part 2. So the big question in quantum mechanics that nobody really understands, well, until you understand this model anyway, is that why should particles be best represented as probability distributions? And now you see that they couldn't be rendered any other way, because a bottom-up model is just intractable. It's too complex. It doesn't work well. It takes way too much calculation. It's inefficient. No conscious computer would dare do something that sloppy that takes that long. You know, it's that inefficient. So what it does is it has this mostly deterministic underlying rule set. And from that, it creates accurate distributions. And all of what we see and interact with and do, even our double slit experiments that are done on tiny particles and so on, they're all done at the probability level. So particles are probability distributions because that's the way reality is rendered. It's rendered in terms of probability. That's why the double slit works the way it works. It works that way. The reason the particles have to come out, those particles with no which way data have to come out in a interference pattern, is because otherwise our reality would have a wrinkle in it. It would have an inconsistency in it. And the system rule says no inconsistencies, a good reality that has no logical inconsistencies. So they had to come out that way. System had no choice. So once you see that our reality is a virtual reality, that it's being run in a consciousness computer that is a subset of the larger conscious system configured as a computer, that's our rendering engine, and that's being done at the probability level, then all of the big secrets about quantum physics just fall right out. It's a probability distribution because everything at that level is a probability distribution. Everything's rendered that way. Our whole virtual reality is rendered that way. And it had to come out with that particular distribution because otherwise there'd be a logical inconsistency in the reality. So that's why the double slit works the way it does. And if you just follow the logic, you'll be able to predict the outcome of these quantum experiments without shutting up and doing the math. All you have to do is look at the logic and you'll see how it comes out and you'll know why it comes out that way. You got to follow the logic of the experimental setup. Every experimental setup has an innate logic. According to the rule set says only certain things can happen. And you have various components and they all have to abide by the rule set. And you look at the logic and then you do the probability and there's your answer. So if you want to see actually that delayed eraser done this way, go get the MBT LA 2016. And I went through that. That's where I got these slides. So you'll find that later on in the program. All right, so that is the summary of what we're doing. I guess one thing I haven't said yet is about relativity. Okay, the big paradox in relativity is, why is c a constant? If you understand that the speed of light is always a constant, no matter how fast or slow the source of the light is, it always goes at a constant, then you can get special relativity with a little algebra. Now, general relativity basically was a search for a model of gravitation that could also keep track of relativistic effects, like the special relativity effects. And the Newton model of gravitation really didn't allow that. So this idea of having stretchy space-time, where you put a big weight and space-time stretches like a trampoline, there is no stretchy space-time. That's a model, okay? Problem is that if physicists just never forgot that that's a model, they'd be fine, but they begin to believe in their models, that their models are real, and that space-time, the stretchy space-time out there, when mass gets around it, it deforms the space-time. They think that's really happening. It's a physical thing. It's not. It's a virtual reality. It's all about information. It's not about stretchy space-time. You make a measurement, you get a result. And that result is going to come out of a random draw from a probability distribution of the possibilities. That's the results you're going to get. Okay. I guess we're done. Thank you, everybody. We're done with it. So now we have the MBT Science Trilogy. It's really not all MBT science. There's other science. There's the science that we're doing in quantum physics at Pomona. There's more science actually going on in MBT than what I've just said, but this is the basic, the underlying framework. So here we actually have seen consciousness deriving physics. You see, because people often don't know where to put consciousness. Consciousness they put up at the top of the pyramid as, kind of the most rarefied things that the physical world can create, but it's actually at the bottom pyramid, and all the physical stuff is built on top of a substrate of consciousness. So we've seen now, if you understand consciousness is fundamental, that consciousness is the computer that computes this virtual reality, then you'll understand why C has to be a constant, because you can only move one delta X every delta T in the simulation. That's as fast as anything can move through this virtual reality. Every virtual reality has its own speed limit, which is 1 pixel of distance for 1 pixel of time. Can't move contiguously also through a virtual reality any faster than that. That's the speed limit. So that's the speed of light. Nothing goes faster than that. That's all our resolution supports. Now, we can increase that resolution by making both delta T and delta X smaller by the same amount. And that happens sometimes. That's why C changes just a little bit out in that 8th or 10th decimal place, because we do that. So that's basically the fundamentals of relativity, is C is a constant. Okay, so we know that. And now we see that the double slit experiment, Schrödinger's cat, the Zeno effect, how all of these are easily described and understood once you see that this is a probabilistic reality. Consciousness is the computer. So from that perspective, everything becomes both simple and elegant. Well, this is Tom Campbell. Thanks for listening. Over and out. MBT Events hope you liked this video. We now have well over 1,000 hours of free video on this user-friendly, ad-free YouTube channel. Though these videos are free to our viewers, they represent many thousands of hours in production and editing, and many thousands of dollars invested in video and audio equipment, along with the required computers and software to store and process the raw video into finished products. So far, all of this content has been funded directly out of our own pockets. Be assured, we will always continue to do what we can. It's our life, our purpose, a labor of love that we will continue to pursue as best we can. However, those pockets are not as deep as they used to be. Thus, we are now seeking to augment our resources with support from our viewers. If you find something of significant value in our videos, please consider supporting their production through our newly created Patreon account or through a one-time donation. The links are in the description below. Thank you.